Hello everyone, this is Adnan and welcome to Chemistry with Adnan. In this lesson, we will be covering chapter number 5. This is 5.1 exothermic and endothermic reactions. I just want to tell you that on this YouTube channel, I'm covering the entire IGCSE Cambridge Chemistry 0620 syllabus, and I'm also covering the other exam boards such as AQ and A and EdXL. So if you are registered with AQA or EdXL, so you can find your relevant playlist and you will see that the entire syllabus is covered there. I also offer one-on-one tutoring lessons. If you need any assistance with chemistry, you can fill the Google form that is linked in the description and I will contact you. So the first topic is core state that an exothermic reaction transfers thermal energy to the surroundings, leading to an increase in the temperature of the surroundings, right? So this is, you have to develop an understanding that, for example, like what is an exothermic reaction? Exothermic reaction is the one that releases heat to the surroundings, right? So we can study this using some examples. Let's say you have, a cup of coffee. It's a hot coffee base, placed on a table, and it is releasing heat into the surroundings. So what will happen, the air surrounding this cup will get hotter, and the coffee itself, it will get colder over time, right? So remember, whenever exothermic reactions they take place, the substance that is releasing heat, it gets colder. The temperature of the system goes down, and the temperature of the surroundings, it goes up, right? So this is an example of exothermic reaction. Another example will be like burning, combustion, right? Burning of fire and others. So now we move on to the next one. State that an endothermic reaction takes in thermal energy from the surroundings, leading to a decrease in the temperature of the surroundings. So yeah, so now, for example, if we have, and this is a system where the system absorbs heat from the surroundings, right? So what will happen? As a result, the temperature of the surroundings will will go down, and the temperature of the substance itself, it will go up, right? So what is an example of endothermic reaction? So uh, you know photosynthesis can be the example of an endothermic reaction, and thermal decomposition reactions are endothermic reactions. So for example, citric acid, reaction of citric acid and sodium hydrogen carbonate, right? When they react, so they absorb energy from the surroundings. So this is the difference between an endothermic and exothermic reaction. So an exo means outside, so heat is released, right? So heat is released, and endo means inside, or like here heat is absorbed. Yeah. So, and in exothermic reaction, the heat of the system, it decreases, and in endothermic reaction, the heat of the system, it increases, right? So this is the definition or concept of exothermic and endothermic reactions. Now we move on to the third subtopic, which states that interpret the reaction pathway diagrams showing exothermic and endothermic reactions. Yeah. So here on this axis we plot energy, and that's the progress of reaction, right? So I'm going to write here progress of a reaction. Okay, so remember that okay, I'm drawing this one for exothermic, that for exothermic reaction, the reactants, they are always higher than the products, right? So let's say reactants are here. So the products will be lower than the reactants, right? So you can say that either reactants are higher than the products or products are lower than the reactants, or you can say that reactants, they have a higher energy than the products, and products, they have a lower energy than the reactants. So these are the few ways that where you can define this in a diagram, right? So these are reactants and these are our products. So we can say that reactants are higher in energy than products. We can also say that the products are lower in energy than the reactants, right? So these are the ways where you can define this. So this is called the energy profile diagram. For endothermic reaction, it is going to be the opposite. And you can pause this video and try to draw the diagram by yourself, and you will figure it out that you will see, if you have drawn it like this, that the products are higher in energy than the reactants, then it is correct, right? These are reactants and these are the products, and this is a diagram for endothermic reaction. All right, so now we can say that for endothermic reactants will be lower in energy than products, or you can also say that products are higher in energy than the reactants. So it's the complete opposite of the exothermic reaction. Okay, so there are a few things that we need to understand in this one, and um, yeah, I think that's it for like core students. You don't need to know the delta H thing, but let me just explain. So remember that starting from the reactants and all the way up, the highest point on the graph. So this is the activation energy. What is activation energy? It is the minimum amount of energy that is required for a reaction to occur. And here, what will be the activation energy? Remember that activation energy always start from the reactants, right? So, and it goes all the way to the highest point on the curve. So this is the activation energy, right? And the difference between the reactants and products, this is called delta H, the enthalpy change. So that is delta H. Delta H is the enthalpy change. And for this one, between the reactants and the product, the difference between the reactants and the products, that is, delta H, right? So yeah, so I hope this is clear. Now we move on to the next one. State that the transfer, now this is the supplement subtopic. Those students who are registered for the extended exam, you will be assessed on these topics, right? So state that the transfer of thermal energy during a reaction is called the enthalpy change, delta H of the reaction. Delta H is negative for exothermic reactions and positive for endothermic reactions. So I think I've already explained delta H here, the difference between the reactants and the products. So all we need to know is that delta H is negative for exothermic reaction. This negative sign means that the energy is being given out, and here delta H for endothermic reaction is going to be a positive value, right? So yeah, so I think this is clear as well. And now we move on to the next part. It says define activation energy as the minimum energy that colliding particles must have to react. So I think we have already talked about this as well, that it is the minimum amount of energy that is required for a reaction to occur, right? So this is the definition, that the minimum energy that the colliding particles must have to react. So I think, yeah, so I don't think there's anything to talk about this. And but I think I can explain this a bit. So imagine, like, like you must have prepared a barbecue many times, and we mostly use charcoal to to cook the barbecue as a source of heat, as a source of fire. So if you take a piece of charcoal from the bag, from a bag of a charcoal, so and if you place it in your palm, and if you hold it in your hand, it's not gonna burn by itself, right? It is still reacting with, let's say this is a piece of charcoal, and the oxygen molecules from the air, they are still colliding with this piece of charcoal in your hand, but it doesn't light up, right? It doesn't catch fire by itself. So you have to heat it. So this is an example of activation energy. So why the reaction is not taking place while you are holding it in your hand, where it is still, colliding with the water, like oxygen molecules from the air. The reason is that it doesn't have the activation energy. So the oxygen particles in the air and the charcoal itself, its molecules or its atoms, they are at a lower energy state, right? So when you heat it a bit, like you have a fire starter, or coal burners and stuff. So like you put, usually we put a small wooden piece in here when we are when we are trying to burn charcoal. So it's so what's the purpose of that? It's gonna increase the energy of these particles, and once they reach a certain level, and at that point when they collide, the reaction starts to happen, right? I hope this is clear. Now uh, 6, this is a subtopic 6, which states that draw and label reaction pathway diagrams for exothermic and endothermic reactions using information provided, including reactants, products, enthalpy change of the reaction, and activation energy, blah, blah, blah. Okay, so this will be explained more effectively when we will solve questions from past papers, but let me just explain it to you. So let's say we have this reaction N2 plus H2. So a reaction like this will be given to you on the exam, and this one is producing ammonia. So nitrogen is a gas, hydrogen is a gas, and ammonia is also a gas. To balance this, I'll have to put 2 here and 3 here. Now the equation is balanced. Okay, so now you have to draw the energy profile diagram. So how will you figure out whether the reaction is exothermic or endothermic? So they may give you, and they may tell you that in the question that the reaction is exothermic. So look for the word exothermic, or they may say that during this reaction heat is given out, right? Or they may not use any of these words, and instead they give you the delta H value of this reaction. So if that is negative, it means that it is going to be an exothermic reaction. And so for endothermic reactions, they may use the word endothermic in the question, or they may use this phrase that heat is being absorbed, and or if they give you the delta H value, so it will, if it is positive, then that means that the reaction is endothermic, right? So this is what they try to figure out. They make sure that you understand this or not, right? This is what you will be assessed on. So now this reaction, this is exothermic, is, and delta H is negative. And yeah, so now you have to draw the diagram for this, right? So now we know that the reaction is exothermic because delta H is negative. So now how will I draw the diagram? So I will start from any random area, any random point on this axis on which we plot energy, and you will write your reactants. So N2 plus 3H2, right? And then you go up, this graph goes up like this, and then you come down, and you must come down from the reactants, right? And you can stop anywhere, um, you know from down from the reactants, right? So here you're going to write the products. So ammonia, NH3, 2 NH3. So this is how we plot the energy profile diagram for an exothermic reaction. And now we have to label. Okay, we have already labeled, we have already written the reactants. So these are the reactants, and these are the products, or a product. And then the enthalpy change. So I've explained it before, that the enthalpy change is the energy change between the reactants and the products, right? So yeah, so these are reactants, and these are the products. So this difference, that is delta H, the enthalpy change. And the activation energy is the highest point on the graph starting from the reactants, right? Like this. So I hope this is clear. Yep. And you label it as E sub A, activation energy. Okay, so this is how you will have to answer these questions, right? Now, topic number 7, state that bond breaking is an endothermic process and bond making is an exothermic process, and explain the enthalpy change of a reaction in terms of bond breaking and bond making. All right. Okay. So you need to understand that, uh, yeah, that whenever bonds are formed, so energy is released, right? So bond formation is always exothermic, and bond breaking, it's an exothermic endothermic reaction, right? Endothermic. Yeah. So bond formation, it is exothermic, and bond breaking, it is endothermic. Let me explain why. This is something which confuses many students and even some teachers. I've seen here, where I teach, that they don't have understanding for this. Like especially biology teachers, when they explain that breakdown of glucose releases energy. So they believe that energy is released when glucose molecule is being broken, which is not the case. That is totally wrong. So remember that you should ask yourself that why atoms they make bonds. They make bonds so that they can come on a lower energy level, right? So what does it mean? That the two hydrogen atoms that are not bonded together, they will have a higher energy. And when they make a bond, so let's say this is distance between these two atoms, and that's the energy. So when they come closer at a certain distance, so they're here, they will form H2 molecule. So the H2, the energy of the H2 molecule will be much lower than the energy of individual hydrogen atoms. So this is the whole concept of making bonds. That is why atoms make bonds, so that they can become stable and they can come on a lower energy level. So during this process, the energy must be released, right? How do they come on that lower energy level? So by releasing that energy into the environment, into the surroundings. So once a bond is formed, and now in order to break it, or in order to bring these atoms back to their high energy state, original state, you have to provide energy, right? So you have to break this bond. In order to break this bond, you must provide energy, and then the bond will be broken, and these two individual hydrogen atoms, they will absorb that energy, and they will go back to their initial high energy state. So this is the main concept. And as I'm explaining this, so you will 100% understand that why like how this works in chemical equations, right? So let me just read this one more time to make sure that I'm not skipping anything. State that bond breaking is an endothermic process, yes, and bond making is an exothermic process, and explain the enthalpy change of a reaction in terms of bond breaking and bond breaking. Yeah. So, whenever a chemical reaction takes place, let us take example of the reaction that we, uh, wrote above. So N2 plus H2, and that is producing ammonia. So remember that on the reactants side in a chemical reaction, on the reactants side bonds are broken, right? These bonds are broken, and here the delta H will be a positive value because energy is being absorbed in order to break these bonds. And once these atoms are free, and then they rearrange and they create something new. So on the products side, bonds are formed, right? Bonds are formed, and the delta H will be negative, right? So now you can see here that in all chemical reactions, bonds are broken and bonds are formed, right? So why is that some reactions they end up being exothermic and some other reactions they end up being endothermic? Now let me explain. So if the heat, this is very important, so I want you to pay attention. So if the heat absorbed is greater than the heat released, right? So we have two scenarios. So if the heat absorbed is greater than the heat released, right? Uh, Let me just write it like this. Heat absorbed while the bond breaking process on the reactant side, heat absorbed is greater than the heat released. The reaction ends up being endothermic, right? Because it is absorbing more heat and it is releasing less heat. So the net energy change will be endothermic reaction. This reaction will end up absorbing heat from the surroundings. And if heat absorbed is less than the heat released, like more heat is being released and products are produced than it is being absorbed. So the reaction will end up as exothermic reaction, right? So now let me explain that what happens with the glucose. So glucose C6H12O6, when it reacts with oxygen, it produces carbon dioxide and water. So CO2 and H2O. So what is happening? So when the glucose molecule is being broken, it must absorb energy. You must provide energy. That is why if you have studied glycolysis, which is, this is for teachers who are watching this. So in the, process of glycolysis, which is breakdown of glucose, so you, in the first step, ATP is consumed, right? This reaction, the first step, it absorbs ATP. And so this is also an indication that this is an endothermic process, not an exothermic process. It's not gonna, the breakdown of glucose, it's not gonna give you energy, but you must provide energy for the breakdown of glucose, right? So this is the reactant side. So bonds are being broken. So when the products are formed, they will release energy which will be higher than the energy that was initially absorbed on the reactant side, and that is how this reaction ends up being exothermic reaction overall, and it releases ATP, right? So this is how it works, right? The breakdown of glucose, it is not going to release energy. You have to explain the whole thing, that how it works, right? So now we will take a look at some numbers in the final topic, which states that calculate the enthalpy change of a reaction using bond energies, right? So let me paste a question here, and we can solve it together. So these are the types of questions that you will uh, see on the exam, and we will uh, practice these questions separately in the second part of this lesson, where I will extensively solve questions on past papers related to chapter 5. So I'm pasting this here. Okay. So the question says that calculate the enthalpy change of the following reaction using the bond energies given in the table. So you will be given a table like this and a chemical reaction, and it's going to tell you that how many bonds are there between these atoms and how much energy is required to break them, right? Or if it's on a product side, how much energy it's going to release. So how are you going to answer this question? So it says calculate the enthalpy change, delta H. We have to calculate delta H, and we have to state whether the reaction is exothermic or endothermic. So look at this reaction. So you have to draw the structure of this molecule. So CH3, CH3. So let me just draw it. So it's carbon and carbon. So sometimes they give you the structure like this, which makes it easier. And this question, it is a bit difficult because some students may not be able to draw this structure by looking at this equation, and it might be a problem for them. And then Cl2, so we have a single bond in chlorine molecule, Cl and Cl. Okay, so these are our reactants. And now the products, again, it's a bit difficult molecule to draw. So carbon with 3 hydrogens. Remember that hydrogens will always be connected to carbon atom, and if oxygen is involved, then one oxygen may be connected to like one hydrogen may be connected to oxygen as well. So then CH2, and then finally Cl. So now you can see that how I drew this. So you see the first unit was CH3, so carbon in the center, and then 3 hydrogens connected to this carbon. And then we have a second unit, which is you know of CH2, again carbon in the center and 2 hydrogens connected to it, and then a chlorine. So this chlorine will also be connected to the second carbon, this one. So this is how you draw the structure, right? And we have another product as well, which is HCl. So plus HCl, we have a single bond between hydrogen and chlorine. All right, now the values are given. So you see, you have to calculate that how many carbon hydrogen bonds do we have on this side, right? So let's count these. Let me just highlight these. So 1, 2, 3, 4, 5, 6. So this is going to be, so carbon hydrogen bond energy is 413. So 413 times 6. This is for the reactants side. You have to calculate it separately for the reactants and separately for the products. So this is 413 times 6. And then chlorine bond, which is like 240, right? So 413 times 6, and then plus, and then yeah, 240, right? And this is the total energy that is being absorbed on the reactants side, right? And the energy is at 3064, right? So 3064 kilojoules per mole. Now you have to do the same for the product side. So you can pause this video and calculate the delta H for the product. I mean the enthalpy for the product side, and see what do you get, right? So how many carbon hydrogen bond do we have on this side? 1, 2, 3. Let me just highlight these again. So 1, 2, 3, 4, 5. So it is going to be 413 times 5 for the products. And then plus we have one carbon and chlorine bond. Carbon chlorine bond is 327. So you write 327 plus we have one hydrogen chlorine bond as well. So plus 428, right? So when you add all this up, you get 3166 kilojoules per mole, right? And that is how you yeah, so now we have the two values. Now the formula that we will be using to calculate delta H is delta H equals to reactants minus products, reactants minus products, right? Or like you can say that the energy absorbed minus energy released, right? So this will be 3064 minus 3166, and that's going to give you negative 102 kilojoules per mole. So now you can see that since the answer, it is a negative and delta H is negative, so it means that this reaction is an exothermic reaction. So this is how you will answer these questions on the exam. So this was chapter 5, and our next lesson in the series will be where we will be practicing past paper questions based on this topic, right? So I would encourage you to join my community on school.com with the name of High School Chemistry. I offer one lesson per month for free, and I also offer group lessons, one-on-one lessons. So you can join the premium package, where you will be able to attend group lessons, like 4 in a month, one lesson per week. And yeah, it is free to join. You can ask questions, you can participate in the discussion forums, you can ask questions, you can reply to questions, you can interact with students from all around the world. So it is an interesting place to be if you are learning chemistry, right? So I hope yeah, so I hope this is clear, and this will be all for today from my side, and I'll see you in the next one. Take care. Goodbye.